Welcome to Fantastic Physics. Today we're going to look at something called the law of conservation of energy, and we're going to do that through the lens of these four ramps here. Now what I have are four marbles, and they are exactly the same mass, the same diameter, virtually identical in every single way. I have four ramps of different colors. We have blue, yellow, green, and red. All of them have different slopes, different ways for the marble to get down to the bottom, but they're all exactly the same height from the desk. So four marbles that are identical, four identical heights, four different slopes. What I'm going to do is use this pipe here to go ahead and line all these marbles up on the very top of the ramp here. And I want to release them all simultaneously. And the question I have for you, audience out there, is which of these marbles will get to the bottom of the ramp first? Will it be the blue one, the yellow one, the green one, or the red one? Let's go ahead and drop them all right now and see what happens. Okay, so if you were paying attention, you would have noticed that the blue one did get to the bottom first, followed by the yellow, then the green, and the red came in last place. So the question is, why did these marbles get to the bottom at such different times? Well, it has to do with the slopes of the ramps themselves. The blue one has the steepest slope right off the bat, so you're going to get the marble to gain velocity very quickly and very early on. This gives it a distinct advantage and causes it to finish early. The yellow ramp is technically the shortest distance to the bottom because it is virtually a straight line for most of the trip, but it's not necessarily the shortest time to the bottom. And that's because this slope is less steep, it's more gradual than the blue one, which means the marble is gaining velocity at a slower rate, and so it falls behind. Then we get to the green ramp, which has an even more shallow slope at the start, which means the marble is gaining velocity at a very, very slow rate. This causes a huge disadvantage. By the time it gets to a steeper slope here in the middle, it is already too late. And then of course we have the red ramp, which is the most shallow slope for most of the trip. And so by the time it actually gets to a meaningful steep slope here, the other marbles have virtually already gotten to the bottom. So it's just too late for it to start gaining velocity. Now, you might have already seen this coming, or maybe you didn't, but here is a more important question for you out there. The question is this. Yes, the marbles are getting to the bottom at different times, but which one has the highest velocity when it does get to the bottom? In other words, when these marbles get down here at the bottom of the ramp, which one is moving fastest? Would it be the blue ramp marble, the yellow ramp's marble, the green ramp's marble, or the marble that goes down the red ramp? And to answer this question, we need to use something called the law of conservation of energy. And let's start with the basics. So if I were to go over here and grab one of these marbles on the floor and bring it back, I know this marble has a particular mass, and I do have a scale here in front of me, so I'm going to go ahead and figure out what the mass of this marble is because that's going to be important. I'm going to put this tape here on the scale just to ensure that the marble doesn't roll away, and then I'm going to zero the scale so that it doesn't weigh the tape, it's just going to weigh this marble. And so what we have is 66 grams. Okay, so I'm going to write this here. The mass of the marbles, 66 grams, which by the way, we're going to convert this to kilograms because we need kilograms in our calculations. We're going to move the decimal 3 places to the left and we get 0.066 kilograms. So that's the mass of our marbles. The next thing we need is the height from the desk to where the marbles were released from. And for that, I'll use this meter stick here. I want to make sure we're not using the inches side. I'm going to go ahead and use the centimeter side. And I'll go ahead and record that as well. So we have, it looks like 30.25 centimeters. So the height, which we will call H, is 32.25 centimeters. Again, I want to convert centimeters into something I can use for an equation, so that's going to be meters. In this case, we're going to move the decimal 2 places to the left or divide by 100. So we get 0.3225 meters. So we have the mass of the marble and the height at which the marble started above the table. One other thing we need to use for our equation is something called G. And G stands for gravitational acceleration. This is the rate at which objects accelerate to the ground when you drop them. And it turns out that for objects on Earth or near the surface of Earth, g is going to be approximately 9.8 meters per second squared. So this is the rate at which objects accelerate towards the ground, or gravitational acceleration. Now that we have these three values, we can calculate what's called gravitational potential energy, or GPE. And gravitational potential energy is equal to the mass of the object times acceleration due to gravity times the height. And so what is GPE? What is gravitational potential energy? Think of it this way. If you take an object and lift it above the ground, it has this type of energy. And this is energy that's stored in the object due to its position above the ground. Well, how do I know this object has energy? Well, it's simple. If I were to drop it, it has the potential to start moving. And so that's why we call this potential energy, because it has potential stored in the object due to its position above the ground. So what I'm going to do is calculate the gravitational potential energy of all four of these marbles. They should be the same, because remember, they have the same mass, the same height, and they're all subject to the same gravitational field, which is Earth's. Okay, so let's go ahead and calculate these gravitational potential energies of the four marbles while sitting on the top of each ramp. So we have this equation here. We're going to go ahead and substitute all three of our values. So the mass is 0.066, 0.066. G is equal to 9.8 meters per second squared. And then H is 0.3225 meters, 0.3225. And if I take my calculator out and plug in all of these values, let's do that here. 0.066 times 9.8 times 0.3225. That will give us 0.209. So I'm going to go ahead and round to three places after the decimal. 0.209. And so what are the units of gravitational potential energy? They're called joules. Joules. You can also abbreviate that as J. So what I know is that all four of these marbles have 0.209 joules of gravitational potential energy at the top of the ramps. Okay, so we know all the marbles started with the same amount of potential energy at the start, and that was 0.209 joules of gravitational potential. But the question is, how can we figure out which one's faster at the bottom? Well, we need to use something called the law of conservation of energy. And that law tells us that energy cannot be created or destroyed. In the case of these ramps here, what that means is the amount of energy we had at the beginning should be exactly equal to the amount of energy at the end when they get to the bottom. Well, what kind of energy did they have at the bottom? Well, they didn't have any more height down here, because that's what we called zero height, which means they had no gravitational potential energy. Instead, they had something called kinetic energy, or as we abbreviate, KE. So kinetic energy is the energy associated with motion. Basically, if you have an object that's moving, you know it has kinetic energy. Well, the question is, how much kinetic energy do these marbles have when they get to the bottom? Well, we have an equation for that, and it's equal to 1/2 mv squared, where m is the mass of the marble, v is the velocity of the marble at that position, and that value is squared. Okay, well, here's another question. Can we solve for this velocity v? And the answer is yes. And that's because we know that the kinetic energy the marble has at the bottom of the ramp is exactly equal to the potential energy it started with at the top. And so we're going to say that the kinetic energy was exactly 0.209 joules. And that's because, again, energy can't be created or destroyed. It can only be transferred from one form to another form of energy. And so if this is true, we can now look at our equation and plug this value in on the left side for KE. On the right, 1/2 times the mass of the marble, which was already measured before, that was 0.066, times v squared, where v is unknown, and we're going to solve for that. First thing I would do mathematically is 1/2 times this value is going to give us 0.033. And on the left side, we still have this number. The next thing I would do is divide both sides by 0.033, and that's because we want this value to cancel out on the right so that we can solve for v squared. So we have v squared is equal to this number divided by this number, and if I plug that in my calculator, I get 6.333. So v squared is 6.333. Well, if I want to solve for v, I have to take the square root of both sides. That's going to give me the square root of 6.333. And so my final answer, if I type that into the calculator, I get 2.517. 2.517 meters per second. And what's remarkable about this value is it's very, very, very close to the real velocity of these marbles at the bottom. Now, it is going to be a little bit different because in reality, there is some friction in the system. Friction causes some of the marble's energy to turn into heat, and that's energy being released from the system, which would result in a slightly lower velocity at the bottom, but it's really not much. And because it's such a low friction system and it's such a short distance, we can safely ignore the effects of friction, and we're still going to get a very, very accurate number here. So what does this tell us? Well, all the marbles started with the exact same potential energy, which means they all should have ended with the exact same kinetic energy, which means they all should have the exact same velocity at the bottom of the ramp. So the answer to our initial question in this video is all the marbles have the same velocity down here. Despite the fact that the blue marble gets there first, it's still going to be moving with the same speed as all the others when they get to that position. Okay, so now that I know that the marbles all have the same velocity at the bottom of the ramp and they're all moving at this velocity, 2.517 meters per second, I want to share with everybody out there that there is a shortcut method that can calculate those velocities in one single step. So let's take a look here. Gravitational potential energy, we said is mgh. We said that kinetic energy is 1/2 mv squared. And more importantly, we said that the law of conservation of energy guarantees that the amount of energy I have at the top of the ramp at the start must equal the amount of energy this marble has at the bottom of the ramp, assuming that there's little to no friction and friction can be ignored. So if that is true, then this energy, the GPE at the beginning, should be equal to the kinetic energy at the end. And so I should be able to set these two equations equal to each other. So GPE equals KE. And the next thing that we're going to notice is there's an m on both sides. So the mass can actually be canceled mathematically because it's the same quantity on both sides. We get G times H equals 1/2 times V squared. Oops, made a little mistake. There's no m here anymore. So it'll be 1/2 V squared. And then what I can do is multiply both sides by 2 so that the 1/2 goes away. So we have 2GH equals V squared. And my final step is take the square root of both sides, and that will allow me to solve for V. And so I get this new equation that came from setting these two equal to each other. And so my equation is V equals the square root of 2GH. That means if I take 2 times Earth's gravitational acceleration, which is 9.8, times the height of the marbles at the beginning, and I take the square root of that, I can actually calculate their velocity at the bottom in a single step. So let's go ahead and plug in our values. 2 times 9.8. Their heights were measured at the start. That was 0.3225 meters. And if I take my calculator and plug all of this in, we get 2.514. 2.514 meters per second. Notice that this value is virtually identical to the value that we got in the other method. They're only off by about 3 thousandths, which is a very small amount, and that's due to rounding from the previous step. So very, very similar, basically identical. Both methods work really well. And if you wanted to test this in reality, you can take a motion sensor. This is actually a photo gate. And what a photo gate does, this one has 2 lasers. And as the marble, so if you put this at the bottom of the ramp, as the marble rolls through the photo gate, it passes the first laser, and then shortly after it passes the second laser. And this photo gate can calculate the velocity using this equation here, distance divided by time, because it knows the distance between the two lasers, and it will be able to get a timestamp for when it hit each laser. So it also does a very accurate velocity calculation, and maybe I'll show that in another video, but basically you would put this gate at the bottom of all 4 ramps and test them, and what you should find is that velocity should come out to be virtually identical to these two. There may be small differences due to the actual friction in the system that I did mention before, but it's very, very small and extremely accurate.